A function is a mapping, but a mapping isn't necessarily a function, though we often use the terms interchangeably. Let's look into that. A mapping or function is a rule which assigns elements from one set to another. The domain is the set that we start in, and the codomain or target set is the set where we end. We take elements from the domain as input, apply the mapping, then get outputs in the target set. Let's look at this function. We can see that we map the Cartesian product of the natural numbers, or any ordered pair xy of natural numbers, to the set of rational numbers, through the rule that the output is 1 over the sum of the inputs. This function helps us show a very important property for mappings. It's that the rule must work for every element in the domain. Imagine that our domain is the Cartesian product of the integers instead of the natural numbers. In that case, we could put the ordered pair -1, 1 through our rule, and our output would be 1 over 0, which is undefined. It's very important that we check our mapping so that it's valid, and instances like this don't occur. So what's the difference between a mapping and a function? A function is a specific type of mapping that assigns exactly one output to each input, whereas a mapping arbitrarily assigns elements from the domain to the codomain. This means that if you have a function and input a single x, you'll get a single y. But if you have a mapping and input a single x, you could get multiple y's. Let's look at this. Do we think that this is a function or a mapping? This right here is a mapping. See how this input is assigned to two different outputs? That property is not allowed when working with functions. Looking at the relationship between inputs and outputs, we can define more properties of mappings and functions. A mapping is said to be injective or one-to-one if for all x and y in the domain where x does not equal y, then the mapping of x does not equal the mapping of y. This means that you can only map one input to one output. No two elements can be mapped to the same output. We can think of this intuitively by looking at a diagram. Every point that is mapped to in the target set has only one input element. A mapping is said to be surjective or onto if for all y in the target set, there exists an x in the domain that can be mapped to y. This means that you must be able to map something to any element in the target set. We also have a diagram for this. You can see that every element in the target set is mapped to by an element in the domain. But don't all mappings do this? Well, no. If we have a mapping where x rules to x plus 3, and our domain and target set are both the natural numbers, then the smallest number that we can input is 0. So if we input 0, we'll see that our output is 3. But wait, our target set is the natural numbers, which includes 0, 1, and 2. But there doesn't exist an input that we can pick that will map to either of those values. That means that this function isn't surjective. A bijection is a mapping that is both injective and surjective. That means that every point must have exactly one output. Visually, in a bijective mapping, every element of the domain maps to one unique element in the codomain, and every element in the codomain is covered. Now that we understand injective, surjective, and bijective mappings, we can develop geometric tests to see what's what. Take note that when working on a Cartesian plane, our x-axis represents our domain or inputs, and our y-axis represents our target set or outputs. If a function is a mapping where each input is mapped to exactly one output, that's like saying for every input on the x-axis, we get one output on the y-axis. If we want to test this, we can draw a vertical line down the graph. If the mapping is a function, then that line should only ever intersect the graph once. If we look at this graph, we can see that our vertical line intersects the graph twice, which means that there are two y outputs assigned to one x input. Therefore, this graph cannot be a function, and it is a mapping. We can do a similar thing for the other properties. If an injective mapping is one-to-one, then if we draw a horizontal line across the graph, we should see it intersects the graph at most once at any position, as to show that no y value is mapped to by multiple x values. We put emphasis on the fact that the line should intersect the graph at most once, because the line could not intersect the graph at all, and that would still be completely valid. If a surjective mapping is onto, then that means that every y value is mapped to by an x input. So if we draw a horizontal line across the graph, the line must intersect the graph at least once at any position, as to show that every y value ends up being mapped to. And if a bijective mapping is both injective and surjective, well, we know that being injective means the horizontal line should intersect the graph at most once, and being surjective means the line should intersect the graph at least once. So if both properties hold, then a bijective mapping should have the line intersect the graph exactly once at any position. While these geometric approaches are helpful, there are situations that you can't rely on visualizing a mapping for. In such cases, you'll need to use logical reasoning or written proofs to verify the properties of the mapping. When proving injectivity, we want to prove that for all x, y in our domain, where x does not equal y, then f of x does not equal f of y. To prove this, we use a direct proof and show that if f of x equals f of y, then the variables x and y that we defined are actually equal. If we look at this example, is the function 2x plus 3 injective? Well, let's attempt that direct proof. If we say that f of x1 equals f of x2, that's like saying 2 times x1 plus 3 equals 2 times x2 plus 3. We can cancel the 3's on both sides, and again cancel the 2's on both sides, and we're left with the statement x1 equals x2. What we just proved is that if we ever have a situation where x1 and x2 map to the same output, then x1 and x2 are actually the same variable. When proving surjectivity, we want to prove that every element in the target set is mapped to. To prove this, we'll show that for any output we want, we have an input that maps to it. If we look at the same function as before, 2x plus 3, if we define the function to map elements from the set of real numbers to the set of real numbers, then we want to show that for any arbitrary element a that is in the real numbers, we can map an element to it. So, with the function 2x plus 3, we say that a equals 2x plus 3. From here, we want to show that there exists an x value that maps to this. If we move 3 to the other side, then divide by 2, we can isolate that x. What we've just done is we've found the element that will map to a. If we plug in the expression a minus 3 over 2 into our function, then we can cancel the 2's and again cancel the 3's, and now we have a, the arbitrary element that we wanted to map to. This shows that for any element a in the target set, we have an x input that will map to it. Therefore, this function is surjective. Let's try it again here with the function x cubed plus x. If we say that the arbitrary element a is equal to x cubed plus x, we can subtract by x, but now we're stuck. We can't reduce any further. We can try dividing by x, but that doesn't get us any closer to the expression that we want to get. In this case, we can't write out our proof in the same manner that we did before. So we need to switch directions. Let's take a look at our function x cubed plus x. This is a polynomial, specifically a polynomial of degree 3. A property of polynomials with odd degree is that they go off to both positive and negative infinity. If we graph our function, we can see that every element in the target set, or the y-axis, is covered, since the function goes off to positive and negative infinity. Therefore, our function is surjective. Now, pulling the two together, proving bijectivity is just proving both injectivity and surjectivity. Now, we can go through all the steps that we did previously and show that the function is both injective and surjective, or we can use this great property of bijections, and that is that for every bijection, there exists a unique inverse. So if we find an inverse to a function, then we can prove that the function is bijective. If we go back to our previous example, let's find an inverse for it. If we say y equals 2x plus 3, then subtracting by 3, we get y minus 3 equals 2x. Dividing by 2, we get y minus 3 divided by 2 equals x. This is our inverse function. If we apply our mapping to an input x, then apply our inverse mapping to that, we'll get back to x, and we can see that everything will cancel out very nicely. Therefore, since our function has an inverse, it is bijective. We have discussed how to prove these properties, now let's discuss how to disprove them. You just show a counterexample. The counterexample is extremely powerful, as it immediately nullifies the validity of the statement that was just made. If you hear all swans are white, all you need to do is show the existence of one swan that isn't white, and it entirely dismantles the statement. Let's look at this example now. Is the function x squared injective? Well, if it's injective, then every output must have only one input that maps to it. But look at this. If we map positive 2, we get positive 4. And if we map negative 2, we also get positive 4. This contradicts the idea that the function is injective, and therefore it's not. Let's try testing surjectivity. Well, if our function is from the real numbers to the real numbers, then we might have an idea. We can look at the output negative 1. Negative 1 is in the real numbers, but if we have the equation x squared equals negative 1, we have no real solutions. There are no real numbers that can map to negative 1, so the function is not surjective. Let's quickly discuss composite functions before we go. If we have a function f and another function g, we can define a composition that combines both of the functions by taking the output of f as the input of g. We denote the function g of f of x as to show off the nature of taking the output of f as the input of g. We can also do it the other way around. If we take the output of g as the input of f, then we would have the composite function f of g of x. The key requirement for composite functions is that the target set of the first function must match with the domain of the second function, since to apply the mapping, its inputs need to be valid. If we have a function f defined as x plus 2 and another function g defined as x squared, then g of f is defined by putting f as the input to g. In this case, g of f is x plus 2 squared. This works because the domains and target sets for each function is the real numbers, so the sets line up for our composition. We can also take the composite function in a different order, where we take f of g, which is x squared plus 2. We can see that the order we use for our composition affects the output of our compositions.